Right, good afternoon, 1023. The purpose of this video is to show you the apparatus that goes with this afternoon's theory tutorial. So what I've got here is two cylinders. They're identical, they're the same size, but the one is solid and the other is hollow. I want you to think, if I were to drop them and the air resistance was not significant, which would hit the ground first? Well, you know that they'd both fall with the same acceleration, so they'd hit the ground at the same time. But what about if I roll them down a ramp? So I've got a ramp here, and we're going to have a race to see which one hits the bottom first. Okay? So think about it for a moment. Which one would you expect to get to the bottom of the ramp first, or would you expect them to both go at the same rate? Let's have a look. So I'm going to start them both in the same position. Ready, steady, go. Okay, so we have a winner. The solid cylinder went faster than the hollow one. What about take two cylinders that are both solid, but one is bigger than the other? These two cylinders are made of wax, so different diameters, but identical in all other respects. Okay, so let's see what happens then. Okay, who do you think is going to win the race? Ready, steady, go. Okay, they both reached the end at the same time. Okay, one more example. What about if I take the cylinder, the wax cylinder and the aluminium cylinder that are the same size? So the only difference is mass. Okay, who do you think is going to win? Ready, steady, go. Again, we have a tie. All right, you're going to have the opportunity to think about why that is when you work through the example. Okay. All right, the second example is a ballistic pendulum. This is a ballistic pendulum. And what it's used to do is to find the speed of a bullet. So here I have a bullet, and I'm going to shoot it with this gun here. When that happens, the bullet is going to hit the pendulum, and the pendulum is going to swing up. So we've got two things that happen. Firstly, there's a collision between the bullet and the pendulum bob, and then secondly, there's a swing. Okay? So straight away, you should be able to think of conservation of momentum, conservation of mechanical energy. All right, so let's see what happens when it goes. 1, 2, 3. Okay, just to show you that the bullet is actually inside here, here it comes out. Okay, good. The third piece of apparatus is the roller coaster, which you have seen before. Here we go. Here's a ball that I release, and it does a loop and goes around to the other side. Okay. The question is, what is the speed of the ball at different heights? What's it at the top of the loop? What is it at the bottom of the loop? And then another question, an optional challenge at the end, is there a minimum height from which it needs to be released in order to go around the loop? And if so, what is that minimum height? There we go. All right, so the last piece of apparatus that I want to show you, there isn't a question on the tutorial about it, but it's still a fun piece of apparatus to look at, is another race. So what we've got is two different tracks that balls can roll down. And the question is, who wins the race? Okay, now you can see that both balls start with the same potential energy. They both end with the same potential energy. And so you'd expect that the difference in potential energy would be converted to the same kinetic energy. So they both leave the ramp with the same speed. But do they both get there at the same time? Does energy have anything to say about the time that it takes? So who are you betting on? Are you betting on the green ball, the red ball, or both of them getting there together? Think about that for a moment. All right, let's see how it goes. Did you get it right? Did you bet on the right ball? Well, what happens, of course, is that the ball on this side initially accelerates faster. So its speed gets faster early on. So it gets ahead in the race, and the green ball never quite manages to make it up. Let's have a look again. Ready, steady, go. Okay. So what we can conclude from that is that although the balls have the same kinetic energy at the end, the energy transfer that we calculate doesn't tell us anything about the time that that energy transfer takes place.